Good evening, friends. Welcome to day 12 of the Six Sigma Masterclass Elite sessions. So, today we'll be looking at a very interesting concept called design of experiments, which will be under the improve phase. And then we'll work out an exercise under DOE. And towards the end of today's session, we will work out some three exercises under control charts. And then the final 60 minutes will be taking up the black belt final assessment. So this is going to be the agenda for today. So let's get started. So let me just share my screen and we are going to look at the design of experiments under improve phase. So let me click on improve. So just below the FMEE notes, we will find DOE, design of experiments. Fine. So DOE as a concept was introduced by Ronald Fisher, by a quality expert by name Ronald Fisher, and it was popularized by a Japanese quality expert, Jenichi Taguchi. In fact, Taguchi is much more famous than Ronald Fisher. So even though Fisher introduced this concept, but it was Jenichi Taguchi who actually popularized this concept by identifying the application opportunities, right? So he actually identified some practical application opportunities for this design of experiments concept. So he popularized it. So that's how Jenichi Taguchi became much more famous than Ronald Fisher. So what exactly we do in design of experiments? So as the name itself suggests, so we would be conducting series of experiments in a controlled environment with the sole objective of identifying the experimental factors and their respective levels, which would actually provide the optimal output. Say, for example, if you are preparing a new dish, right? You have invented a new dish and you are preparing that dish in the kitchen. So obviously you'll do a lot of experiments, right? So you will mix and match all these spices and then salt, oil, etc., right? And you'll try to find out which combination actually provides the best taste as far as the dish is concerned, right? The same way we will be considering the process related factors and then we will kind of mix and match these process related factors at a predetermined levels and try to find out which combination of factors and the levels provide the best possible output, right? So that is exactly what we will do in design of experiments. So since we need to conduct all these experiments in a very controlled environment, so DOE is a very costly affair, right? So we will not use DOE for some simple problems. So only if the problem is pretty chronic, in the sense the problem has been in existence for a very long time. So we will perform the design of experiment, right? So let us take an example. So since we are quite obsessed with coffee preparation. In fact, I'm quite obsessed with coffee preparation because this is something I've been giving as example right from day one, right? So let us take the same example on the final day as well. So the process is coffee preparation. And let us assume that the response variable will be the taste or the quality of the coffee. So let us not worry about how this is going to be measured. So let us assume that is the taste of the coffee or quality of coffee will be measured in terms of some numerical value, right? So what I need to do in order to conduct the experiment, first and foremost, I need to identify the experimental factors which I feel will be having a huge influence on the taste of coffee. Because taste of coffee or quality of coffee is the output that I have recognized. So I'm going to identify the experimental factors which is likely to have a bigger influence on the taste or quality of coffee. So I have picked up a couple of experimental factors. So there could be some other better experimental factor, I do not know, just for an example. Okay. So the first experimental factor that I have considered is the temperature at which the coffee is heated. And the second experimental factor that I have considered is quantum of coffee powder. So I believe that these two experimental factors might have a huge influence as far as the taste or quality of coffee is concerned, right? So when we conduct the experiment, we need to have minimum of two experimental factors, right? So these are all the minimum numbers that I'm telling. So we need to have minimum of two experimental factors. So we can have any number of experimental factors, right? But minimum of two experimental factors. And once I have identified the experimental factors, the next step would be to identify the levels for these experimental factors. Again, I need to fix two levels, minimum of two levels for each of these experimental factors, right? So I need to come up with minimum of two levels for each of these experimental factors. Suppose I fix the levels for temperature as 15 degrees centigrade and 20 degrees centigrade. I sincerely do not know whether coffee will be heated at this temperature. I'm just throwing some random values. Okay. And then the quantum of coffee powder, I fix the levels as 5 mg and 10 mg, right? So how many levels I have fixed for each of these experimental factors? Two levels. So now what I need to do, having fixed the experimental factors and also the levels for these experimental factors, next we need to come up with the experimental design, right, for conducting the experiment. And that is what we would call as treatment combinations or experimental runs. So treatment combinations or experimental runs is nothing but the experimental design that I need to consider for the given scenario, right? So we have two factors, each at two levels. These are the minimum numbers that we are supposed to consider for conducting an experiment, right? And when we have two levels for both these factors, so how many treatment combinations we can arrive at for this scenario? So we simply need to multiply the number of levels that we have fixed for each of these experimental factors. So two levels for each factor, so 2 into 2. So total will be four treatment combinations that we need to arrive at for this particular scenario. So what are the four treatment combinations? First one, temperature, I will keep it at 15 degrees centigrade, that is level 1. And coffee powder, I will have it as 5 mg, right, which is again level 1 for coffee powder. And then the second combination will be temperature, I will retain it as 15 degrees centigrade, but coffee powder, I will change it to level 2, 10 mg. And then the third combination will be temperature. I'm going to change it to 20 degrees centigrade, but then I will revert the coffee powder back to level 1, which is 5 mg. And the final one, both the factors at level 2, temperature at 20 degrees centigrade and coffee powder at 10 mg. So these are the four possible combinations that we can arrive at for this scenario wherein we have two experimental factors each at two levels, right? So we will have total of four treatment combinations or experimental runs. So if you are going to express these factors in terms of A and B, and then level 1 and level 2 as 1 and 2, then the combination can be written like this. So the first combination is like A1, B1. That means both the factors at level 1. And the second combination is like A1, B2. That means the factor A is at level 1, but the factor B is changed to level 2. And the third combination is A2B1, which means the factor A has been changed to level 2 and factor B has been reverted back to level 1. And the final combination will be A2B2. That means both the factors are at level 2, right? So with this experimental design that I have created, I can now perform the experiments and then analyze the output data and find out which particular treatment combination provides me the best taste as far as coffee is concerned, right? So this is how I will perform and analyze the experimental data. So another example. So let us look at another example. So it's not essential that we need to have only two factors considered for the experiment. As I told you, we can consider any number of experimental factors, but minimum we need to have two factors. Similarly, we can have any number of levels fixed for these experimental factors, but then minimum we need to have two levels fixed for each of the experimental factor. So another important thing to be noted here is we don't have to fix equal number of levels for all the experimental factors, right? So it's not necessary that we need to fix equal number of levels for all these experimental factors, and we can always have a particular experimental factors with 3 levels and the other experimental factors with 2 levels. So the next example actually, provides a scenario like this. So wherein the response variable is considered as mileage given by a car. So what are all the experimental factors that might have an influence on this response variable? So speed at which the car is driven will definitely be one of the key experimental factor. And then the type of gas, right, could be another factor, and the service, whether it is done or not, right? So these three are considered as experimental factors for this particular scenario where the output variable is mileage given by a car. Now, what I'm doing here, I am fixing 3 levels for the speed at which the car is driven. So, car driven at 50 kilometers per hour, 70 kilometers per hour, 90 kilometers per hour. But then I'm going to have only 2 levels for the type of gas, that is A and B, and 2 levels for service done, whether it is yes or no. Now, here we find we have 3 experimental factors, but the levels for these experimental factors are not equal. So we have unequal number of levels fixed for experimental factors, and we can also, kind of fix unequal number of levels for the identified experimental factors is absolutely fine. Now, how many treatment combinations we will have for this scenario? So we simply need to multiply the number of levels that we have fixed for each of these experimental factors. So speed at which the car is driven, we have 3 levels. Type of gas, 2 levels. And then service done or not, again 2 levels. So the total number of treatment combinations that we can actually form for this particular scenario will be 3 into 2 into 2. So 3 into 2 is 6, 6 into 2 is 12, right? So you need to write down all the possible 12 treatment combinations that we can actually create for this scenario. So sometimes what will happen if you are new to this particular concept, it would be very difficult. If you have only two factors each at 2 levels, writing down all these 4 treatment combinations is not going to be challenging, right? So you can also write this in terms of A and B and level 1 and level 2. But then you have a scenario wherein there are 3 experimental factors, and one of the experimental factor we have 3 levels, and the other two we have only 2 levels. So these kind of unequal levels fixed for the experimental factors, it will be very difficult for us to write the treatment combinations right straight away. So what we can do in these kind of scenarios, so if you have higher number of experimental factors or higher number of levels, so you can actually create a decision tree like structure. So since factor A, that is the speed at which the car is driven, we have fixed 3 levels for it. So I will have A1, A2, A3 written like this, right? And then factor B, that is type of gas, we have only 2 levels. So I will branch B1 and B2 from A1. Similarly, B1 and B2 from A2 and B1 and B2 from A3, right? And since C is also, factor C is also couple of levels, so I can branch C1 and C2 from B1 and C1 and C2 from B2. Similarly, C1 and C2 from B1, C1 and C2 from B2, C1, C2, C1, C2. Now I need to follow the path. That's it, right? It looks like a decision tree like structure. So I just need to follow the path. So what is the first path? A1, B1, C1. So A1, B1, C1. The next path is A1, B1, C2, right? And the third one, A1, B2, C1, and then A1, B2, C2. So A1 part is over. Now moving on to the A2 part. A2, B1, C1, A2, B1, C2, A2, B2, C1, A2, B2, C2. Now A2 part is over. Now moving on to the A3 part. A3, B1, C1, A3, B1, C2, A3, B2, C1, and finally A3, B2, C2, right? So these are the various treatment combinations that I can create for this scenario. So let us see if we have 12 treatment combinations identified for this scenario. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the 12 treatment combinations have been listed down here, right? So this particular scenario will have 12 treatment combinations. So to arrive at the number of treatment combinations, what we are supposed to do, we simply need to multiply the levels that we have fixed for all these factors so that we will be able to list down all possible treatment combinations for a given scenario, right? But then in case we have three experimental factors identified, each at two levels, right? So how many treatment combinations we can arrive at in total? So there will be 2 into 2 into 2. So three experimental factors, each at two levels means 2 into 2 into 2. So which will be 2 into 2, 4, 4 into 2 is 8. So we will have total of 8 treatment combinations, right? So we will have A1, A2, and then B1, B2, and then C1, C2. So what are the possible combinations? A1, B1, C1 is one combination. A1, B1, C2 is the next combination. A1, B2, C1 is the third combination. A1, B2, C2 is the fourth combination. So A1 part is over. Now moving on to the A2 half. A2, B1, C1, A2, B1, C2, A2B2C1 and A2B2C2, right? So if you find it difficult to list down all these 8 treatment combinations in one go, as I told you, we can always create this decision tree like structure. So since we have all the three experimental factors, each at two levels, so I will have A1 and A2 in two different halves. And then from A1, we will have B1, B2, from A2, B1, B2, right? So from B1, C1, C2, from B2, C1, C2, here again, C1, C2, C1, C2. Now I need to follow the path A1, B1, C1, A1, B1, C2, A1, B2, C1, A1, B2, C2. And then A2 path, A2 half. So A2 B1 C1, A2 B1 C2, A2 B2 C1, and then finally A2 B2 C2. So we have 8 treatment combinations. So 1, 2, 3, 4, 5, 6, 7, right? So when you create a structure like this, you won't be missing out any of the treatment combinations. So you can fill in all possible treatment combinations for a given scenario. So this is how we will arrive at the number of treatment combinations and also list down all possible treatment combinations, which is nothing but your experimental design. And this will be considered for conducting the experiment, right? And then the next terminology that we are going to look at is factorial effect. So you already seen the treatment combination or experimental run. So the next terminology that we are going to look at is factorial effect. So what is this factorial effect? So factorial effect is the ultimate impact that will be created on the response variable by the experimental factors, either on its own or in combination with the other experimental factors, right? Say, for example, in the coffee preparation scenario, right? So, what are the experimental factors we have considered? The temperature at which the coffee is heated and also the quantum of coffee powder, right? So, if you really look at these experimental factors, so temperature at which the coffee is heated as a main factorial effect could be impactful, right? Temperature on its own can create that impact with regard to the taste of coffee, quite possible. And also the quantum of coffee powder as a main factorial effect. that is on its own, can create that impact as far as the taste of coffee is concerned. Or since we have two experimental factors, the interaction effect is also possible. So temperature into quantum of coffee powder can also interact together and then create that wonderful impact as far as the taste of coffee is concerned. So there are three factorial effects that we can identify for the scenario wherein we have two experimental factors, right? So both the experimental factors has main factorial effect. That means on its own, they can create that impact as far as the taste of coffee is concerned, or they can combine together and create that interaction effect, right? Which would have a huge influence on the taste of coffee. It's quite possible even in while preparing a new dish, right? Sometimes what will happen, the salt on its own or spice on its own may not have a deadly impact as far as the taste of the dish is concerned. But when salt and spice combine together, they can create that interaction effect. So sometimes all these factors may not be significant as a main factorial effect, but they can be significant as an interaction factorial effect. Quite possible, right? So we always used to say in a lighter vein, if you see a kid, and kid is sitting quietly in one corner, so what the parents will say, so don't believe that, he's very quiet. So he is now, all alone and he is very, very quiet. But when he joined hands with his friend, so he becomes very, very naughty, right? So this is the kind of interaction effect. As a main effect, the kid is very, very quiet. But when he joins hand with his friend, the kid becomes very naughty, right? So this is the interaction effect that we can actually see in the kids, correct? So when they join hands with their friend, they will get bold and then they will create lot of nuisance, right? And they will do lot of mischief, right? So this is the interaction effect that we will be able to see. Similarly, when we have these experimental factors, sometimes they may not be impactful as a main factor, but they may be impactful as an interaction factor. So they may combine with some other experimental factor and then create that impactful effect as far as the response variable is concerned, right? So this is exactly what we have mentioned here as part of factorial effect. So these experimental factors can on its own create that impactful effect on the response variable, or it can combine with other experimental factors and create that impactful interaction effect on the response variable. So now the question is how to determine the number of factorial effects for a particular scenario. So how to determine the number of factorial effects for a particular scenario. So we have the formula for that as well. Just like how we would simply multiply the number of levels that we have fixed for the experimental factors in order to arrive at the number of treatment combinations applicable for a particular scenario. We have a formula for arriving at the number of factorial effects applicable for a particular scenario, and the formula is 2 to the power of k minus 1. So here the number 2 is not the number of levels, right? Number of levels do not have any role to play as far as the number of factorial effects determination is concerned, right? So 2 is a constant value and k is the number of factors, experimental factors considered for the experiment, right? So 2 to the power of k minus 1. Suppose we have two factors considered for the experiment, just like the coffee preparation scenario, then how many factorial effects we will have for this? So it will be 2 to the power of 2 minus 1. What is 2 to the power of 2? It is 4. 4 minus 1, 3 factorial effects are applicable for a two-factor experiment scenario. So what are the three factorial effects as we saw just now for the coffee preparation scenario? So temperature as a main factorial effect, and then quantum of coffee powder as a main factorial effect, and temperature into quantum of coffee powder as an interaction factorial effect. So if you have only one factor, then obviously you will not have any interaction effect. But since the design of experiments would require minimum of two experimental factors to be considered, so we will definitely have this interaction effect, right? So which also needs to be validated. So if you have two experimental factors, which is the minimum number that we need to consider for conducting an experiment, so we can have three factorial effects which can be validated. So once we have the experiments conducted for all these treatment combinations, right, and have the value for the response variable, which is the taste of coffee, then we will analyze the data, analyze the experimental data, and then find out which factorial effect is impactful, right? Whether temperature as a main factorial effect is impactful, quantum of coffee powder as a main factorial effect is impactful, or temperature into quantum of coffee powder as an interaction factorial effect is impactful. So we will validate with the help of experimental data. So that is what we will do in design of experiments. So it will be segregated into two parts. The first part is arriving at the experimental design or the treatment combinations or experimental runs, and then conducting the experiment. And with whatever data we have collated for the response variable, we need to perform an analysis and then validate which of these applicable factorial effect is impactful or is significant, right? Whether the main factorial effects are significant or the main factorial effects along with the interaction factorial effect is also significant. So that is what we would validate with the experimental data, right? So here I just given the calculation. So when we have two experimental factors considered for the experiment, so the number of factorial effects will be 2 to the power of 2 minus 1, which is 3. So the three factorial effects in terms of A and B will be A as a main factorial effect, B as a main factorial effect, AB as an interaction factorial effect, right? So what we need to do when we actually perform the data analysis, we need to frame three pairs of hypothesis statements, right? So this is something new for us. As yesterday, even that ANOVA exercise, we had only one factor, but we had three levels for that factor. Production center was the one factor, sole factor, but then we had three categories for production center. So production center A, production center B, production center C. So these three will be the three levels for production center. So in that case, we will have only one factorial effect which can be validated. But here for design of experiments, since we need to have minimum of two experimental factors, so for a two experimental factor scenario, we will have three factorial effects which can be validated. And when we start the exercise for analyzing the data, we will frame three pairs of hypothesis statements, right? So if you have two factors, then there will be three pairs of hypothesis statements. So the first pair will be H naught colon A as a main factorial effect is insignificant versus HA colon A as a main factorial effect is significant, because we need to prove the significance of these factorial effects. The second pair would be H naught colon B as a main factorial effect is insignificant versus HA colon B as a main factorial effect is significant. And the third pair of hypothesis statement will be H naught colon AB as an interaction factorial effect is insignificant versus HA colon AB as an interaction factorial effect is significant. So these are the various pairs of hypothesis statements that I will frame before performing the analysis. Suppose we have three factors A, B, and C considered for the experiment, then how many factorial effects we will have? So we can validate for its significance. So it will be 2 to the power of 3 minus 1. So 2 to the power of 3 will be 8. 8 minus 1, it will be 7. So we will have 7 factorial effects applicable for this three-factor experimental scenario, right? So what are the 7 factorial effects that we can validate? So the first one, A as a main factorial effect, B as a main factorial effect, C as a main factorial effect. So all these main factorial effects are over. Now, the two-way interaction factorial effect. AB as a two-way interaction factorial effect, AC as a two-way interaction factorial effect, and BC as a two-way interaction factorial effect. And finally, the three-way interaction, ABC, as a three-way interaction factorial effect, right? So if you have only two factors, then maximum we will have only two-way interaction. But when we have three factors, maximum we will have three-way interaction factorial effect. So we would be validating all these seven factorial effects when we analyze the data, right? So as part of this, we will frame seven pairs of hypothesis statements to begin with, right? So for each factorial effect, we will frame a pair of hypothesis statements. Fine. So this is about treatment combinations and factorial effects. So treatment combinations for conducting the experiment. Factorial effect is for validating or analyzing the data and validating for its significance. Now, when we conduct the experiment, we need to be aware of the three principles of DOE. Very, very important, right? So the first principle is replication. So what is this replication? So replication is all about having minimum of two sample data points pertaining to the response variable for each treatment combination. Say in this coffee preparation, for each treatment combination, we need to have minimum of two sample data points pertaining to the taste of coffee. So that is what is replication. So why do we need minimum of two sample data points for each treatment combination? Because we need to estimate the error variation. If you remember yesterday, we kind of calculated the error variation and considered that as the base variation for us to validate the significance of the factorial effect, right? The single factor factorial effect. So go back to the exercise file and click on ANOVA sheet. So here you would find the error variation being considered. So this is nothing but the variation within the sample data points for a particular production center, right? So the production center variation is the variation between the mean values of all these three production centers, whereas the uh, error variation will be the variation within the data points pertaining to a particular production center, right? And this is the comparison we made because error variation will be considered as common cause variation. So in order to estimate the error variation, we need to have minimum of two sample data points. So with just one single data point, we will not be able to quantify the variation metric, right? So we need to have minimum of two sample data points in order to quantify the variation metric, and hence we need to have minimum of two sample data points for each of the treatment combination. So this is basically to estimate the error variation, which will be considered as the base variation for us to validate the significance of a factorial effect. So without this error variation, we will not be able to validate the significance of a factorial effect. So if you want to estimate the error variation, then we need to have minimum of two sample data points for a particular treatment combination. And that is what we would call as replication, right? So we can have any number of sample data points, but we need to have minimum of two sample data points for each of the treatment combination. Then only we will be able to quantify the error variation, right? And the next one that we have is randomization. So what is this randomization? So when we conduct the experiment, there could be certain external factors which might be influencing the results of the experiment. So as part of the experiment, so we need to analyze and then find out whether the experimental factor is impactful or not, right? With respect to the response variable. So when can you find out that the experimental factors are impactful or not? Only when we do not have the influence of the external factors, right? So the external factors are going to influence the results of the experiment. Then we will not know whether the change in the result is due to the change in the levels of the experimental factor or due to the influence of the external factor. So the external factor like external temperature, external pressure, etc., can all influence the results of the experiment. So we need to ensure that these, influence of external factors are totally nullified. And that is why we would perform randomization. So when we perform randomization, we will not conduct the experiments in a predefined sequence. Say, for example, these are the four treatment combinations that I have uh, designed for this coffee preparation scenario. It is not as if I'm going to go in the same sequence, right? So when it comes to randomization, I can pick the third treatment combination and conduct the first experiment, and then the first treatment combination, and then the fourth, and then the second. So this is how I will randomize so that I will be able to nullify the impact of the external factors influencing the results of the experiment. So as part of the DOE experiment, we need to validate the significance of the experimental factors only. So if you want to validate the significance of the experimental factors, then it's important for us to ensure that all the other factors are kept constant. But then we cannot control the external factors like external temperature or external pressure. So what we can at the best do, so we can randomize conducting the experiment. When you randomize conducting the experiment, then we will be able to nullify the impact of the external factors influencing the results of the experiment, right? So we will not go in a pre-defined sequence and conduct the experiments. So we will randomly pick a treatment combination and conduct the experiment, right? So it is not as if, we will be favoring a particular treatment combination. Say, for example, so morning time is supposed to be favorable for that process. And if you are going to conduct all possible experiments pertaining to a particular treatment combination during the morning time, then it's very likely that that treatment combination can actually come out on top. So we need to give equal opportunities for the other treatment combinations as well. So we will conduct one round of experiments during the so-called favorable time, and then the next round can be conducted for all the treatment combinations during the so-called not so favorable, time frame, right, for the process. So this is how we would randomize conducting the experiment so that we will be able to nullify the impact of the external factors. And the third principle that we have is local control. So we have already seen how the external factors influence can be nullified. In case of local control, it is about nullifying the impact of non-experimental factors influencing the results of the experiment. Say, for example, in coffee preparation scenario, right? So what are the experimental factors we have considered? Temperature at which the coffee is heated, and then the quantum of coffee powder. And when we conduct the experiment, obviously, we will be preparing the coffee by considering all the other non-experimental factors like milk, sugar, water, etc., etc., right? But then these non-experimental factors are supposed to be maintained at a constant level so that they do not influence the results of the experiment. So the main idea is to identify whether the experimental factors are impactful as far as the taste of coffee is concerned. So from that perspective, if you look at, then we need to ensure that the non-experimental factors like milk or sugar needs to be kept constant throughout the experimentation period. So that is what the local control would actually suggest, right? So these are the three principles of DOE which we need to adhere while conducting the experiment. So replication for estimating the error, so wherein we will have minimum of two sample data points for each of the treatment combination. Randomization is all about conducting the experiments in a random manner so that we are able to nullify the impact of the external factors influencing the results of the experiment. And local control is all about nullifying the impact of the non-experimental factors influencing the results of the experiment. So while the external factors will be called as uncontrollable noise factors, because these external factors, we will not have any control over it, right? And all these non-experimental factors, whether It is external factor or the factors that you are considering for the preparation of the output. So they will be called as noise factors, right? Because they do not have any role to play as far as the experiment is concerned. So we are not going to change the levels for all these noise factors. They are supposed to be kept constant. So those factors which we are supposed to, maintain some constancy will be referred as noise factors, right? And those factors, the experimental factors, which we would allow uh, to change during the course of the experiment at the predefined levels that we have already fixed for them will be called as signal factors. So the experimental factors will be referred as signal factors and all the other factors will be referred as noise factors. So when it comes to external factors, they will be referred as uncontrollable noise factors, whereas in case of non-experimental factors like milk, sugar, etc., they will be called as controllable noise factors because these factors we can easily control. But then the external factors very difficult for us to control the nature, right? So that is why external factors will be uncontrollable noise factors and the non-experimental factors like milk and sugar in coffee preparation will be considered as controllable noise factors. Fine. So we look at a couple of important terminologies here in DOE. The first one is blocking, right? So there can be a question on blocking in the black belt final assessment. So let us understand what exactly is blocking. So blocking is the arrangement of experimental units that are similar to one another in groups or blocks, right? So this blocking will be performed in order to practice local control. Say, for example, you do not have sufficient quantity of milk, right, for the to last the entire experimentation period. So you don't have sufficient quantity of milk to last the entire experimentation period. So you will be forced to buy milk from a different lot, even though it could be from the same supplier, but you'll be forced to buy the milk from a different lot. So when you buy the milk from a different lot, there could be a small difference in the quality of milk. Only if it is from the same lot, right? So we can maintain the quality. So if it is going to be from a different lot, even though it is purchased from the same vendor, then the quality of the milk may slightly differ. So in order to ensure that the change in the quality of milk doesn't really impact the result of the experiment, we need to resort to the blocking technique, right? So that is why I told you blocking technique is resorted to actually practice local control. Now, how this blocking will be done? So let us consider a simple scenario. Two factors A and B, each at two levels, right? So how many treatment combinations or experimental runs we can have for this scenario? There will be four treatment combinations or experimental runs when we have two experimental factors considered for the experiment. So what are the four treatment combinations? So each, factors, experimental factor, we have fixed two levels, right? So there'll be four treatment combinations, 2 into 2. And what are the four treatment combinations? A1, B1, A1, B2, A2, B1, and A2, B2. These are the four treatment combinations that we can arrive at for this two factor, each at two levels scenario, right? Now, how many factorial effects we can have for this scenario? So when we have two experimental factors considered for an experiment, we can have three factorial effects. So what are the three factorial effects? Then A is a main factorial effect, B is a main factorial effect, AB as an interaction factorial effect. So this is similar to that coffee preparation scenario, right? So A, B, and AB, right? Now, all these factorial effects will be placed in separate columns like this. Now, what I'm going to do, I'm going to write contrast values for each of these factorial effects against each of these treatment combinations. So I'm going to write contrast values for these factorial effects against each of these treatment combinations. So if I'm going to write the contrast values for the factorial effect A, I'll be looking at the level of A in a treatment combination. So if the level of factor A is at 1, then I will give the contrast value as minus 1. If the level of factor A is at level 2, then I will give the contrast value as plus 1. So I will not be looking at the level of B as a factor. So when I'm writing the contrast values for A, so I will be looking at the levels that we have for A as a factor in all these treatment combinations. So A at level 1, I will give the contrast value as minus 1. A at level 2 in a treatment combination, I will give the contrast value as plus 1, right? So this is what we call as contrast value, minus 1 and plus 1 being assigned, right? When the factor is at level 1 and level 2 respectively, right? Now, the first treatment combination, I'm writing the contrast values for factorial effect A. The first treatment combination, if you look at factor A, it is at level 1. So factor A at level 1, so I need to give the contrast value as minus 1. The second treatment combination, again, A is at level 1. So what will be the contrast value? Again, it will be minus 1. Third treatment combination, A at level 2. So it will be plus 1. And fourth treatment combination, A at level 2, it will be again plus 1. So if you have written the contrast values correctly, we can validate by summing up all these contrast values, and the answer should be 0. So if we get the answer as 0, post summing up all these contrast values, that means you have written the contrast values correctly. So if you are getting some negative or positive value, that means you have not written the contrast values correctly, right? So again, writing down the contrast values for the factorial effect B against each of these treatment combinations. Now we need to look at the level of factor B in all these treatment combinations. So the first one, B is at level 1. A1, B1 means B is at level 1. So minus 1 will be the contrast value. The second one, B is at level 2. So it will be plus 1. Third one, again B at level 1. So minus 1. Fourth one, B at level 2. So plus 1. Right? So we get the answer as 0. That means we have written the contrast values correctly. Now for AB as an interaction factorial effect, we simply need to multiply the contrast values that we have already written for A and B as main factorial effect. That's it, right? So we get minus 1 into minus 1 plus 1, minus 1 into plus 1 minus 1, plus 1 into minus 1 minus 1, plus 1 into plus 1 plus 1. So here again, we will get the total as 0, meaning that we have come up with the correct contrast values for this factorial effect, right? Now, what I'm going to do in order to create blocks, I'm going to consider AB as an interaction factorial effect. So whenever you are facing constraint while performing the experiment, so what we will try to do, we will always give priority for validating the significance of the main factorial effect. That is very, very important for me. So I will give priority for validating the significance of the main factorial effect, and the interaction factorial effect validation will be sacrificed. So we would be prepared to sacrifice validation of the interaction factorial effect whenever we face some constraint like this. So why do we resort to blocking? Because of this constraint. What is the constraint? The sufficient quantity of the non-experimental factor raw material is not available to last the entire experimentation duration. So that being the case, so what I would be prepared to forego? So I would be prepared to sacrifice validation of the interaction factorial effect in favor of the validation of main factorial effect. So for me, validation of main factorial effect is very, very important. So I would be willing to forego or sacrifice validation of interaction factorial effect. So considering this interaction factorial effects, what I'm going to do, I'm going to group or create blocks of the treatment combinations that would fall under plus 1 as a contrast value for AB as an interaction factorial effect. And similarly, those treatment combinations that would fall under minus 1 as the contrast value for AB as an interaction factorial effect. So considering AB as an interaction factorial effect, so what are the treatment combinations that would fall under minus 1? It is A1, B2 and A2, B1. So A1, B2 and then A2, B1. So what are the treatment combinations that would fall under plus 1 for AB as an interaction factorial effect? It will be A1, B1, the first one and the final one, A2, B2. So these two treatment combinations fall under plus 1 as a contrast value for AB as an interaction factorial effect. So these are the two different blocks that I have created, right? Under minus 1 and under plus 1 for AB as an interaction factorial effect. So what I can do, since I don't have sufficient quantity of milk in our example, so I can use the milk pertaining to a particular lot for conducting the experiments with regard to these two treatment combinations that fall under minus 1 and the milk from a different lot for conducting the experiments under the contrast value plus 1. So conducting the experiments pertaining to these two treatment combinations falling under plus 1, right? So two different lots of milk can be used for conducting the experiments like what I said just now. So for the treatment combinations falling under minus 1, we will use the milk from a particular lot. And for the treatment combinations falling under plus 1, we will be using milk from a different lot because we don't have sufficient quantity of milk to last the entire experimentation period. So through this approach, we would be able to successfully validate the significance of the main factorial effect A and B, but we will not be able to validate the significance of the interaction factorial effect AB, right? So which anyway we would be willing to sacrifice. So this is the blocking technique that we would follow in order to practice local control, which says that we need to nullify the impact of the non-experimental factors influencing the results of the experiment. And the next technique that we are going to look at is confounding. So yesterday in the mock test, you would have got a question on confounding, right? So when the main factorial effects and the interaction factorial effects are identical, then we would call that technique as confounding, right? So let us look at, how to identify the confounding here. So let us consider, three factors, three experimental factors, each at two levels. So we have already, listed down the treatment combinations for this scenario. So three experimental factors, each at two levels. We will have total of 8 treatment combinations. So these are the 8 treatment combinations which we have listed down here, right? And then how many factorial effects we will have for this scenario? So when we have 3 experimental factors, we will have 7 factorial effects. So it will be 2 to the power of k minus 1. So k is 3. So 2 to the power of 3 is 8. 8 minus 1 is 7. So what are the 7 factorial effects? A as a main factorial effect, B as a main factorial effect, C as a main factorial effect, AB as an interaction factorial effect, AC as an interaction factorial effect, BC as a two-way interaction factorial effect, finally ABC as a three-way interaction factorial effect. So how to practice confounding? So what I will do, again, I will provide contrast values for these main factorial effects A, B, and C, right, with respect to all these treatment combinations. So when I'm giving contrast values for the factorial effect A, I'll be looking at the level of factor A in all these treatment combinations. So level of factor A is 1 for the first 4 treatment combinations. So I'll give minus 1 for the first 4 treatment combinations. So next 4 treatment combinations A at level 2. So I'll give plus 1 for the next 4 so that the total is 0. Now for B, as a factorial effect, I need to look at the level of factor B in all these treatment combinations. So the first two treatment combinations, B at level 1, so it will be minus 1 for the first two treatment combinations. And the next two, B at level 2, so it will be plus 1. And again, B at minus 1 So next two will be -1. The final two be at level 2, so it will be +1, right? And if you look at C, it actually changes levels in an alternate way. So C1, C2, C1, C2, C1, C2, like that it continues. So it will be -1 +1, -1 +1, -1 +1, -1 +1. Right? So once we have written the contrast values for the main factorial effects, so we can easily, calculate the contrast values for the interaction factorial effect. So if we are calculating the contrast values for the interaction factorial effect AB, then we need to multiply the contrast values we have written for A and B for a particular treatment combination. So if it is -1 into -1, it will be +1 here. So like this, I have calculated the contrast values for all these interaction factorial effects. Now, what I'm going to do if I want to practice confounding, so I would again be willing to sacrifice validation of the higher order interaction factorial effect. So in this scenario, so which one will be considered as the higher order interaction factorial effect? This three factor interaction effect. So three-factor interaction effect ABC will be considered as the higher order interaction factorial effect. So first and foremost, why do we need to practice confounding? Because when we have so many treatment combinations to be considered, we will not be able to conduct the experiments pertaining to all these treatment combinations, right? So we may not have the resource to conduct the experiments covering all these treatment combinations. So whenever we have higher number of experimental factors considered or higher number of levels considered for each of these experimental factors, then we will not be able to consider all possible treatment combinations for that scenario, right? So what we will do, we will consider only a part of these treatment combinations for conducting the experiment, and that is what the confounding will help us to achieve. Another important thing is if you are validating the significance of the main factorial effects, that is more than sufficient. We will be able to replicate the same result for the corresponding two-way interaction factorial effect. So you can save lots of time, right? So you don't have to really validate all these main factorial and two-way interaction factorial effect. It's enough if you are validating the significance of the main factorial effect, we would be able to replicate the same result for the corresponding two-way interaction factorial effect. So we will be able to find out which main factorial effect is confounding with which two-way interaction factorial effect when we kind of perform this exercise. And for that, since I'm going to sacrifice validation of the higher order interaction factorial effect, that is ABC, so I will use ABC as the uh, reference point here, as the reference factorial effect, and I'm going to filter. So filter the data, and taking ABC into consideration, I'm going to choose +1 as the contrast value, right? So if you're choosing +1 as the contrast value, so we can, come up with the confounding, you know, factorial effects here. So if you look at A, right, the factorial effect A, so whatever, factor settings that we find for A, so what are the factor settings here? -1, -1, +1, +1. So the same factor settings are found in the two-way interaction factorial effect BC. BC also has the factor settings -1, -1, +1, +1. So I can say that A as a main factorial effect is confounding with BC as an interaction factorial effect, right? Similarly, if you look at B, we have the factor settings as -1, +1, -1, +1. And if you look at AC, we have the factor settings as -1, +1, -1, +1. So B as a main factorial effect is confounding with AC as a two-way interaction factorial effect. Similarly, if you look at C, what is the factor setting? 1, -1, -1, 1. And for AB, it is again 1, -1, -1, 1. So C as a main factorial effect is confounding with AB as a two-way interaction factorial, right? So this is how we can identify the confounding of the main factorial effects with the two-way interaction factorial effects. So through this exercise, so we are considering only a part of the treatment combinations, right? So we are considering only 4 treatment combinations out of 8 for conducting the experiment, number 1. And number 2, we will be able to just validate the significance of the main factorial effects. That's it. The same result can be replicated for the corresponding interaction factorial effect. Suppose we find A as a main factorial effect is significant. What we can do, we can replicate the same result for BC as an interaction factorial effect. So if A as a main factorial effect is significant, then BC as a two-way interaction factorial effect also will be significant. On the other hand, if B as a main factorial effect is insignificant, then AC as an interaction factorial effect also will be insignificant. So it is enough for us to validate the significance of the main factorial effect. We will be able to replicate the result with the corresponding two-way interaction factorial effect. So that is the advantage that we'll get when we perform this confounding exercise. But what is the sacrifice that we need to do? We need to sacrifice validation of this higher order interaction factorial effect, which is the three-way interaction factorial effect ABC in this scenario, right? So that is what I have summed up here. So A as a main factorial effect is confounding with BC as an interaction factorial effect. B as a main factorial effect is confounding with AC as an interaction factorial effect. C as a main factorial effect is confounding with AB as an interaction factorial effect, right? So since we have started looking at fractional factorial experiments. So we need to know the difference between full factorial and fractional factorial experiments, right? So full factorial experiment is where we would be considering the entire set of treatment combinations applicable for a given scenario. Whereas in a fractional factorial experiment, we will be considering only a part of the treatment combinations for our experiment, right? So by considering the part of the treatment combinations for our experiment, we would be able to successfully validate the influence or the significance of the applicable factorial effects, right? Say in this confounding technique, we are considering only these 4 treatment combinations for conducting the experiment, wherein we would be able to, come up with the results with regard to the significance of the factorial effect A, and the same result can be replicated to from two-way interaction factorial effect BC, right? So this is the advantage that we will have when we resort to this confounding technique. The same way, when we have too many experimental factors considered for the experiment, it will be practically impossible for us to conduct a full factorial experiment. Say, for example, you have something like, say, 8 experimental factors, each at 2 levels, right? So how many treatment combinations we will have for this scenario? It will be 2 to the power of 8. It will be 256 treatment combinations. And if you need to conduct minimum of 2 experiments, because we need to have minimum of 2 sample data points for each treatment combination. So if you want to conduct minimum of 2 experiments for each treatment combination, then we need to conduct a staggering 512 experiments in a controlled environment. So is it practically possible? Definitely not. So when we have higher number of experimental factors or higher number of levels considered for the experimental factors, we need to perform what is called fractional factorial experiments. So we cannot afford to consider the entire list of treatment combination. We need to consider part of the entire list of treatment combination, and then that will become the fractional factorial experiments, right? So a couple of fractional factorial designs that we need to be aware of, because you can get questions on this in the final assessment. So one fractional factorial design is resolution 5 design. So resolution 5 design and Plackett-Berman design. So let us first look at resolution 5 design, and then we will see the Plackett-Berman design. So we're not going to go deep into this. So since there will be a couple of questions on this, so I'm just giving you piece of information with regard to these fractional factorial designs. In case of resolution 5 design, as the name itself suggests, we will have 5 experimental factors considered for the experiment. So resolution 5 design means we will have 5 experimental factors considered for the experiment. Now, how to find out the confounding aspect of this resolution 5 design? So how to find out? So which factorial effect is confounding with what factorial effect is something that we would be able to identify in this resolution 5 design. And for that, we need to consider 5 fingers on one of your hand, right? So 5 fingers on one of your hand. So each finger will represent an experimental factor, right? So what are the different combinations we can actually come up with? So you can separate out one finger and combine the rest of the 4 fingers. So it is like the main factorial effect will be confounding with the 4-way interaction factorial effect, right? And then what we can do, we can combine 2 fingers on one side and the balance 3 fingers on the other side, which means the two-way interaction factorial effect will be confounding with three-way interaction factorial effect. So this will be the confounding technique when we have the resolution 5 design. So resolution 5 design, we will have 5 experimental factors. So when we have 5 experimental factors, the confounding technique will be the main factorial effect will be confounding with 4-way interaction factorial effect. Two-way interaction factorial effect will be confounding with three-way interaction factorial effect. So we need to sacrifice 5-way interaction factorial effect. So if you have 5 experimental factors, the higher order interaction factorial effect will be 5-way interaction factorial effect, which we will obviously sacrifice, right? So this is the resolution 5 design. So they will ask you, what will be the confounding aspect of the resolution 5 design? So we need to pick this option. So let me just make this in bold font. The same option has to be picked as the correct choice or the correct option, right? So resolution 4 design, now that we have seen resolution 5, so we will also look at resolution 4 and resolution 3. Even though we may not get any question pertaining to resolution 4 and 3, let us just look at it. So resolution 4 design means what? We will have 4 experimental factors considered for the experiment. So just consider 4 fingers, one of your hand. So what are the different combinations that we can come up with? So we can separate out one finger and then combine the rest of the 3 fingers. So which means the main factorial effect will be confounding with three-way interaction factorial effect. That is one combination. Next combination, we can combine 2 fingers on one side and the other 2 fingers on the other side. That means two-way interaction factorial effect will be confounding with the other two-way interaction factorial effect. So this will be the confounding technique adopted for resolution 4 design. So 4-way interaction factorial effect will be, that is validation of 4-way interaction factorial effect will be sacrificed. And then resolution 3 design. The resolution 3 design, just consider 3 fingers in one of your hand. So what are the combination that we can come up with? So we can separate out one finger and combine the other 2 fingers. That means the main factorial effect will be confounding with the two-way interaction factorial effect. So in resolution 3 design, we would be willing to sacrifice validation of three-way interaction factorial effect. And this is exactly what we actually considered for this confounding example, right? So we considered 3 factors. It's like resolution 3 design, right? So what is the confounding technique? So the main factorial effect will be confounding with two-way interaction factorial effect. So this is what is written here. Main factorial effect will be confounding with two-way interaction factorial effect. And we will be willing to sacrifice validation of the three-way interaction factorial effect in resolution 3 design. But then you can get a question only on resolution 5 design. And then the next design that we have is Plackett-Berman design. So yesterday itself, you might have been asked a question with regard to the minimum number of experimental runs that we are supposed to consider for a Plackett-Berman design. The correct answer is 12, right? But in the black belt final assessment, you will be asked how many experimental runs are applicable when we have 36 as the number of factors in a Plackett-Berman design. So how many experimental runs are applicable when we have 36 as the number of factors in a Plackett-Berman design? So for that, I have created this template wherein you can just enter the value for n in multiples of 4. So if you have, say, 8 as the number of factors, or the n value is 8, then for number of factors 8, 9, 10, 11, right? Number of factors 8, 9, 10, 11. We will have 12 experimental runs. So these are the minimum number of experimental runs that we would consider for a Plackett-Berman design, right? Suppose we have, say, 12 as n value, then for number of factors 12, 13, 14, 15, we will have 16 experimental runs. Suppose we have 16 as the n value, then for 16, 17, 18, and 19 as number of factors, we will have 20 experimental runs. Suppose we have 20 as the n value. So for 20, 21, 22, 23 as the number of factors, we will have 24 experimental runs. And for 24 as the n value, for the number of factors 24, 25, 26, and 27, we will have 28 experimental runs. And for 28 as n value, for the number of factors 28, 29, 30, and 31, we will have 32 experimental runs. And then for 32 as the n value, so for number of factors 32, 33, 34, and 35, we will have 36 as the number of experimental runs, and then 36 as the n value. So for the number of factors 36, 37, 38, and 39, we will have 40 experimental runs. So the question will be for 36 as number of factors, how many experimental runs is applicable in a Plackett-Berman design? We need to pick the answer 40. So I leave the template as it is so that you can easily pick the answer for that particular question, right? So let us end our discussions with regard to DOE concept. So we will now work out an exercise under DOE. So we will click on the next sheet titled Design of Experiments, DOE, right? So we have a scenario provided here along with the experimental data. So we need to analyze the impact or the significance of the factorial effects applicable for this scenario. So what is this scenario? So it says the below matrix pertains to the time taken to access a website, and the two experimental factors considered for this exercise are internet service provider and browser type. So we are talking about average accessing time as the response variable, right? So when you kind of click on a web link or a website, so how fast you'll be able to access that website. So what would be the impactful factors? So the impactful factors could be the internet service provider and the browser type, right? So these two have been considered as the experimental factors for conducting the experiment. So perform an experiment and analyze the data to identify the significance of the factorial effects, right? So the experiment has already been conducted and we have the data for each of the treatment combination provided here. So if you look at internet service provider as factor A, we have two levels, A, B, C, and XYZ. Browser type as factor B, again has two levels, Edge and Chrome, right? So two-factor experiment, each at two levels. How many treatment combinations we will have for this scenario? Four treatment combinations. 2 into 2, total of four treatment combinations, right? So in terms of A and B, how will you write these treatment combinations? So the first treatment combination is like A1, B1. The second treatment combination is like A1, B2. And the third one is like A2, B1. And the fourth one is A2, B2. So these are the four treatment combinations possible for this particular scenario, wherein we have two experimental factors, each at two levels. And for each of these treatment combinations, we have four sample data points, which is more than sufficient for us to estimate the error variation. So as I told you, if you are going to practice replication, so we need to have minimum of two sample data points for each of the treatment combination in order to estimate the error variation, which will be considered as the base variation for us to validate the significance of the factorial effect, right? We have four sample data points for each of these treatment combinations. Fine. Now, before performing the analysis, we need to frame the hypothesis statements. So for that, we first need to determine how many factorial effects we can validate for this particular scenario. So when we have two experimental factors, right, considered for the experiment. So how many factorial effects can be validated? So here in this case, internet service provider as a main factorial effect, browser type as a main factorial effect, internet service provider into browser type as an interaction factorial effect. So there are three factorial effects that we can validate for a two-factor scenario, right? Or a two experimental factor experiment. Fine. So internet service provider as a main factorial effect, browser type as a main factorial effect, internet service provider into browser type as an interaction factorial effect. So let us frame all these, three pairs of hypothesis statements. So the first pair, H naught colon, internet service provider as a main factorial effect is insignificant, because significance is what we need to prove, right? So I will frame the null hypothesis as the factorial effect is insignificant. Insignificant versus HA colon internet service provider as a main factorial effect is significant, right? So what will be the second pair of hypothesis statements? So H naught colon browser type as a main factorial effect is insignificant versus HA colon browser type as a main factorial effect is significant, right? So what will be the third pair of hypothesis statement? H naught colon internet service provider into browser type as an interaction factorial effect is insignificant versus HA colon internet service provider into browser type as an interaction factorial effect is significant, right? So you'll not get the exercise as a question in the final assessment, but we need to know how to tackle this case scenario. So these are the three pairs of hypothesis statements I will frame. And now I can perform the analysis. So what I need to do, again, I will have the ANOVA table wherein I would need to calculate the sum of squares, degrees of freedom, the mean sum of squares, and then I will calculate the F calculated value for all these factorial effects and then see whether any of these factorial effect is significant or not. So when we calculate the sum of squares, we need to first find out the grand total square by n value. Grand total square by the sample size. So this will be sum of all these data points square divided by how many data points we have in total. So 4 per treatment combination. So 4 treatment combinations are there. 4 into 4, 16 data points are there. So just keep it aside. We will use it for calculating the sum of squares. So the sum of squares for internet service provider, right? So what we need to do, so we need to segregate this as level 1 and level 2. So for internet service provider, ABC is level 1, XYZ is level 2. So ABC data points are there in the first and second row, and XYZ data points are there in the third and fourth row. So I will combine the first and second row, and then I will combine the third and fourth row separately. So let me just sum up all these data points pertaining to the first and second row, which belongs to ABC as a internet service provider. Right? The whole square divided by how many data points I have considered? 8 data points. So divided by 8. Right? So plus the third and the fourth row. This whole square again divided by 8. So the entire thing will be subtracted from the grand total square by n value to arrive at the sum of squares. Now for browser type, right? So browser type, I have Edge and Chrome as the two levels. Edge level 1 and Chrome is level 2. So Edge values are there in the first and third row, and the Chrome values are there in the second and fourth row. So let me just combine the first and third row. Right? The whole square divided by 8 plus the second and the fourth row. Whole square divided by 8. So the entire thing should be subtracted from the grand total square by n value. Right? And then for the interaction factorial effect, internet service provider into browser type. So I would be summing up all these data points pertaining to each of these 4 treatment combinations separate for this. So this plus the first row, this plus this, the whole square divided by 4, right? I'm considering only 4 data points. And then the second row plus 11.7 plus 11.8 plus 11.7, the whole square divided by 4 plus the third row 11.4 plus 11.6 plus 11.6 plus 11.5, the whole square divided by 4 plus the fourth row 10.4 plus 10.5 plus 10.4 plus 10.6, the whole square divided by 4. So the entire thing should be subtracted from the grand total square by n value, which is in cell A36. Right? So from this, we should not only subtract the grand total square by n value, but we should also subtract the sum of squares of the main factorial effect. Right? So sum of squares of the main factorial effect also needs to be subtracted from this. Then only you'll get the interaction. Sum of squares factorial, sum of squares for the interaction factorial effect, right? So this will be the sum of squares for the interaction factorial effect. And as we did yesterday, before calculating the error sum of squares, we'll calculate the total sum of squares. So total sum of squares, we need to square all these individual sample values and sum it up. So the first row, data points. And now the second row, data points. Put a bracket. Plus 11.8 square plus 11.7 square plus the third row 11.4 square plus 11.6 square plus 11.6 square plus 11.5 square plus 10.4 square plus 10.5 square plus 10.4 square plus 10.6 square. So this entire thing should be subtracted from the grand total square by n value, which is in cell K36. Now I can find the error sum of squares, which will be total sum of squares minus sum of the factorial effect sum of squares. This will be my error sum of squares, right? Now degrees of freedom. So how many levels are there for internet service provider? Two levels are there. So it will be 2 minus 1. And how many levels are there for browser type? Again, two levels. 2 minus 1. And for internet service provider into browser type, you simply need to multiply the degrees of freedom that I have calculated for the main factorial, right? And before calculating the error degrees of freedom, so what will be the total degrees of freedom? So we have total of 16 sample data points. So 16 minus 1, the total degrees of freedom will be 15. So the error degrees of freedom will be 15 minus sum of the degrees of freedom we have calculated for the factorial effects. So the error degrees of freedom will be 12, right? Now I can calculate the mean sum of squares, which will be sum of squares divided by the degrees of freedom. And now I can calculate the F calculated value, which will be mean sum of squares divided by the mean sum of squares of the factorial effect divided by the error mean sum of squares. So the error mean sum of squares can be freezed because that is going to be a constant denominator for the other factorial effects as well, right? So as we can see, the F calculated value for the main factorial effects seems to be very high. So we can easily say that the internet service provider and browser type as main factorial effect seems to be significant. But then for the interaction factorial effect, the F calculated value seems to be somewhat less. So it may not be greater than the table value. So we can say that the interaction factorial effect is not all that significant. But then let us reconfirm by calculating the table value. So F dot INV, open bracket, 95% is the confidence level. So degrees of freedom for the factorial effects is 1, comma, degrees of freedom for error, it is 12. So as we expected, the table value is 4.75 and we find the calculated value for the interaction factorial effect less than the table value. So the main factorial effects, we have the F calculated value greater than the table value. So if you are going to calculate the p value, right? So it is 1 minus F dot dist, open bracket. So we need to provide the F calculated value as the reference, comma 1, comma 12, comma, cumulative will be true. So p-value is 0 for the main factorial effects, whereas p-value is 0.064 for the interaction factorial effect. So p-value less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis and conclude that the main factorial effects are significant. So since p-value for the interaction factorial effect is greater than 0.05 for 95% confidence level, we will accept the null hypothesis and conclude that the interaction factorial effect is insignificant. So this will be our inference. So since p-values for the main factorial effects, internet service provider and browser type are less than 0.05 for 95% confidence level, we will reject null hypothesis and accept the alternate hypothesis, right? And thereby conclude that the main factorial effects are significant. So since p-value for the interaction factorial effect, internet service provider into browser type is greater than 0.05 for 95% confidence level, we will accept the null hypothesis and conclude that the interaction factorial effect is insignificant. The interaction factorial effect is insignificant, right? So, but then we need to find out at what level these main factors are significant. So, we will have the internet service provider and their levels. So, internet service provider, the two levels are ABC and XYZ. And similarly for browser type, the two levels are Edge and Chrome, right? So for this, what I'm going to do, I'm going to sum up all these sample data points in each and every row. Right? So ABC as internet service provider is in row number 1 and 2. So I'm going to sum up the values pertaining to row number 1 and 2. And XYZ is in row number 3 and 4. Right? Similarly, Edge is in row number 1 and 3. And Chrome is in row number 2 and 4. Obviously, you're talking about time taken to access a website. So whichever has a lesser time, right? So that would be preferred. So internet service provider, we will choose XYZ, right? Similarly, for browser type, we will choose Chrome. This is how we will come up with the final set. So if you are using the template in order to perform the analysis, we simply need to copy paste the values given in the table in this template. That's it. So you can see the ANOVA table getting populated moment you paste all these values. See? So easy, right? We don't even need to perform all these calculations. So you find they have calculated value for internet service provider as a main factorial effect, 89.58. For browser type, it is 64.44. And for the interaction factorial effect, it is 4.15. So p values 0 and 0 for main factorial effect and for interaction factorial effect, it is 0.064. So the inference will be reject the null hypothesis for the main factorial effect and accept the alternate hypothesis which says they are significant. Whereas we will accept the null hypothesis for the interaction factorial effect, meaning the interaction factorial effect is insignificant. Fine. So this is how we will perform the analysis and find out the significance of the factorial effect and also identify the level of the particular factor which would provide the best possible output. Fine. So let us have a 15-minute break now. So when we come back, we'll look at some 3 exercises under control charts. But before that, before you go for that break, so let us have the group photograph taken now. So I would appreciate if you all could come on video for just for a minute, right? So that I can have the group photograph taken. So I will also open my video.
Sorry, I won't be able to join the group photo. My camera is currently not working.
No, no problem. Others, okay then. So you can all smile a bit and then show the victory sign. It's been tough 12 days, right?
Yes,
They put in the hard work.
the
So you
last
should
1 hour
be happy.
victory sign after the last hour.
Yeah. So let me take the photograph. I'll just remove my headphone. Done. Thank you. Thank you.
Thank
You
you.
can go
Thank
for
you,
a break
Sridhar.
now.
Thank you.
Sridhar, will you be sharing this photograph over the
Yeah.
WhatsApp
I'll
group
be
as well?
sending this. No, I'll be sending this through common WhatsApp group.
Okay, great.
Great.
I will
Thank
send
you.
today
Thank you.
itself. Yeah.
Great. Thank you.
Thank you. Hello friends, I'm back. Hope you're all back as well. So let us continue. So let me just share my screen. So we are going to look at the final set of exercises uh, that we have under control charts. So this is the final sheet in the exercise file. So after that, we have the template reference sheet. So you look at some 3 exercises under control charts. And then, as I told you, we will have the final assessment conducted for the black belt certification. So let us look at exercise number 1. So it says, following is the time taken in hours to produce a unit. The data was collected every 1 hour over a period of 20 hours. Validate whether the process is in control. So we have been provided with a table, right, wherein we have the time data provided every 1 hour, right? And we have the subgroup sample size of 3. So when we have subgroup sample size 6 or less than 6, then we can use X bar range chart, right? Range as a measure of variation can be applied if the sample size is 6 or less than 6. So when we have the subgroup sample size 6 or less than 6, we can use X bar R chart for this scenario, right? So if you are using X bar R chart, then we need to calculate X bar and range values for all these 20 hours. So X bar value and the range value. So let me apply the formula is equal to average of the subgroup samples, right? And the range value will be maximum of these 3 values minus minimum of these 3 values. So maximum minus minimum. So I can just copy paste the formula for all the other subgroup samples and we will get 20 X bar values and 20 range values. Now what I will do is I will calculate X double bar. So this X double bar will be the central line in the X bar chart. Similarly, R bar will be the central line in the R chart. So X double bar will be average of all these X bar values. And R bar will be average of all these range values. Right? So I can just provide reference to these values. So the central line in the X bar chart will be X double bar and the center line in the R chart will be R bar. Now, if you want to calculate the upper control limit and the lower control limit for this X bar chart, so we can use this formula. So the central line, which is the X double bar plus A2 R bar, right? So A2 is a sample size constant value. So for subgroup sample size 3, the A2 value is 1.02. So you can access the sample size constant table by clicking on this web link, right? So, but I've already picked the values from there. So A2 value will be 1.02 for subgroup sample size 3. And similarly, for calculating the upper control limit and the lower control limit for the R chart, which is the range chart, we would require D4 and D3 values. So D4 for subgroup sample size 3 is 2.57 picked from the sample size constant table and D3 for the subgroup sample size 3 is actually 0, right? So let me apply all these values and then calculate the upper control limit and the lower control limit first for the X bar chart. So it will be X double bar plus A2, which is 1.02 into R bar. And then for the lower control limit, it will be X double bar minus A2 into R bar, right? And similarly for R chart, the upper control limit will be T4 into R bar. So 2.57 into the center line, R bar value, and the lower control limit will be 0. So D3 into R bar. So D3 is 0, 0 multiplied by any value will be 0. So let us construct the control chart using Minitab. So for that, I will copy paste the entire table, the Minitab worksheet. Let me copy paste the entire table, Minitab worksheet. So the first column, we have the hour reference, and then the second column, subgroup sample 1, subgroup sample 2, and subgroup sample 3. So we need to go to stat, and we have control charts, and these are the control charts for subgroup, variable charts for subgroup. The other name for continuous is variable. So variable charts for subgroup, we have X bar R chart. Click on that, and the dialog box will open. So all the observations for the chart are given in one row of a column, right? Or given in one row of columns. So choose that particular option, and then input the column headers where we have the sample data, the S1, S2, and S3, and then click on X bar R options, and then click on test. So you would remember that we saw some 8 rules for identifying the presence of assignable or special cause variation. So all these 8 rules are given here. So we will say apply all the tests for special causes and click OK at both the places to get the control chart. As I told you, there will be 2 control charts, one for plotting the X bar values and the other one for plotting the range values. So if at all there was presence of any assignable or special cause variation, it would have got indicated by a red color dot. So we don't find any red color dot in either X bar chart or the R chart. So we can say that this process is very much under control. That means the process is influenced only by common cause variation, right? So you can see the X double bar value, which is 0.063017. That is exactly what we also got. R bar value is 0.00095. So you can provide the inference here. So the inference will be there is nil presence of assignable or special cause variation acting on the process. And the process is very much under control. When I say process is very much under control, it means that the process is influenced only by common cause variation. So there is nil presence of assignable cause variation. But then in the final assessment, you will be asked to calculate the control limits for a standard deviation chart. So they would have given the sample size value as 15 and the standard deviation bar as SD bar, which is the central line in the standard deviation chart, as 1.65. So moment we update the value 1.65, we will see the LCL and UCL getting calculated here, right? So these values can be chosen as the right option from the multiple choice, right? So just, I will leave it as it is. So it will be a same question. So wherein the sample size will be 15 and the standard deviation bar, which is the central line in the standard deviation chart, will be 1.65, right? So these will be the control limits for this scenario, right, in the standard deviation chart. So the template is given next to the X bar R calculations, right? Just beside that first exercise, we have the X bar R calculations. Just next to the X bar R calculations, we have the template for the standard deviation chart. So you can pick the LCL and UCL values from this template. Now moving on to the second exercise under control charts. So it says that the following is the data pertaining to the number of defectives, right? And the audited transactions of a BPO process. So we have been provided with the number of defectives for 20 days along with the samples audited. So we need to plot the defectives data, and the samples are varying on a day-to-day basis. So which chart you will use? We will use P chart for this scenario. So the data has been collected over a period of 20 days, and we have been asked to check whether the process is in statistical control. So defectives data with a varying sample size, we will use P chart for this scenario. So for P chart, first and foremost, we need to calculate the P bar value. So the P bar value can be calculated by summing up the defectives count divided by the sum of the samples audited count. So this will give me P bar, which will be the central line in the P chart, right? And with the P bar value, I can calculate the upper control limit and the lower control limit for all the 20 days. So upper control limit can be calculated by applying this formula P bar plus 3 into square root of P bar into 1 minus P bar divided by the sample size, right? So here if you see, all these P bar values will be constant. So let me just freeze the cell containing the P bar value. So it will be the same for all the days. So I'll only allow the sample size to vary. That's it, right? And for calculating the LCL, it will be again P bar minus 3 into square root of P bar into 1 minus P bar divided by the sample size. So I get a negative value for LCL. So all these control limits cannot take negative values. So if at all you get negative value, then we need to make it as 0, right? So LCL cannot take negative values, so you need to make it as 0 in case you get the negative value for the lower control limit. So I'll make a small adjustment to this formula. I'll put maximum of 0, comma this quantum. So in case we get negative value for LCL, it will pick 0 as the value straight away, right? So let me just freeze all these P bar value in this formula. That is going to be constant, right, for all the days. So P bar value has been freezed. And since, it's a negative value, it has picked 0 as the correct value. Now I can just copy paste both these formulas for the other days. Right. So we find LCL value to be 0 for all the days. That means, so we would have got the negative value for LCL for all the 20 days. So that is why it has updated 0 as the LCL value. And the UCL obviously would vary on a day-to-day basis because of the varying sample size. If the sample size had been constant, then we would have used NP chart. And in that case, the UCL value for all the 20 days will be the same. But then since it is a varying sample size, we have different UCL values for all the 20 days. But then since LCL value is a negative, so it has considered 0 as LCL for all the 20 days. So let me just construct the control chart using Minitab for this binary discrete scenario. So let me just copy paste the entire table. So without the calculation of UCL and LCL, right? And then we go to stat, control charts, and these are attribute charts. So attribute is the other name for discrete. So we need to choose P chart, right? So the variables is defectives and the subgroup size is samples audited. And we click on P-chart options and then click on test. As I told you, for discrete data, we will have only the first 4 rules applicable for the discrete control chart. Only for continuous data control chart or the variable control charts, we will have all the 8 rules applicable for it. So in case of discrete data control charts, we will have only the first 4 rules applicable for us finding out the presence of assignable cost variation. Right. So here we see there is no red color dot in this control chart, indicating that the process is very much under statistical control. So the P bar value is 0.01634. That is exactly what we also got, 0.01634. And then the UCL value on the 20th day. So whatever value you find for UCL here, it's on the 20th day. That is the final day. So which is 0.04760. So the UCL value is 0.04760. And as I told you, LCL is 0 for all the days. So if you want to know the UCL value for a particular day, so say for example, you want to know the UCL value for the 3rd day. So you need to keep the cursor on top of this broken bar. So coinciding with the day number 3. So you'll find the UCL value here is 0.04848. So on the 3rd day, we have the UCL value 0.04848. Fine. So let me just copy paste this graph and provide the inference. Again, I will mention there is nil presence of assignable cost or special cost variation acting on the process, and the process is under statistical process control. So if the process is under statistical process control, it would mean that the process is influenced only by common cost variation, right? But then in the final assessment, you will be asked to calculate the control limits for a P-chart scenario. So they will provide the sample size value, the number of defectives, and the P-bar value. So with the help of these 3 input values, we need to calculate the upper control limit and the lower control limit for a P-chart scenario. So I already provided you with the template wherein you just need to update all these input values and you'll get the answer for control limits. We'll just test it out and see. We will pick the data pertaining to the 3rd day. Say 140 is the samples audited. So sample size is 140. Number of defectives is 4. And the historical average, which is the P-bar value, is 0.01634. 0.01634. And we find the LCL to be 0, which is the case for the 3rd day, not only for the 3rd day, but for all the 20 days. And UCL is 0.04848. 0.04848. Perfect. Right? So I can make use of this template for calculating LCL and UCL for a P-chart scenario. So you will get questions pertaining to the control limits calculations for the standard deviation chart scenario. And I've already given the template and I also showed you the calculations for a P-chart scenario and the U-chart scenario, which we are going to see now. So the 3rd exercise, that is the final exercise of this training session, exercise number 3. So it says the data below represents the number of defects of a transaction process for 20 days. So we need to plot the defects data with a varying sample size. So if it is a constant sample size, then we would need to use C-chart for that scenario. But then if it is a varying sample size, we need to use U-chart for this scenario, right? So for calculating, or if you want to obtain the U-bar value, so we need to use the same formula that we applied for calculating the P-bar value. So again, we need to sum the defect count for all the 20 days divided by sum of the sample size count for all the 20 days. So the sum of defect count divided by the sum of sample size count will give you the U bar value. So this will be the central line in the U chart. Now in the same way you can calculate the UCL and LCL values for all the 20 days. So the formula is here, the manual formula. UCL will be U bar plus 3 into square root of U bar divided by the sample size. Right? So the U bar value will be constant for all the 20 days. So let me just freeze the U bar value alone. And I will allow the sample size to vary. Similarly, for LCL, it will be U bar minus 3 into square root of U bar divided by the sample size. So you don't get any negative value for LCL. So you can retain the positive value as it is. The only thing is we need to again freeze the U bar value in this formula. That's it. So we can copy paste the formula for all the other days. Fine. So let me just copy paste the entire table in Minitab worksheet and let me construct the U chart. Let me just erase this and then copy paste the entire table. Right. So we again need to go to Stat, Control Charts, Attribute Charts. Under that we have U chart. Just click on this. So the dialog box will open. The variable is the defects data and the subgroup size is sample size. Click on this U chart options and then click on test and then say that you need to perform all the tests for identifying the special cause and we click OK at both the places. There seems to be some issue with this. Control charts, attribute charts, then the U chart. So the variables is, subgroup size should be the sample size, given the defects as subgroup size. So subgroup size should be the sample size. And then go to U chart options, click on test, say perform all tests for special causes and click OK. Fine. So get this U chart, you see a red color dot. So this red color dot would indicate that there is presence of special cause or assignable cause variation acting on the process. And what is the reason? So the reason could be because there are 6 consecutive data points showing a downward trend, right? So if you see the 6th consecutive data point in the downward trend has been identified as the value which has been influenced by the special cause variation. So 1, 2, 3, 4, 5, 6. So the 6th consecutive data point has been identified as the one which has been influenced by some special cause variation. So it has occurred on day number 16. So the sample 16, and this has been identified as the one influenced by the special cause variation. And it says that they have applied rule number 3 for identifying the special cause variation. So what is rule number 3? So let me just copy paste the chart here, the exercise sheet, and then quickly let us look at the rule number 3. Just have it as it is, but then go to Stat, Control Charts, Attribute Charts, U chart, and then if you look at U chart options and click on Test. So what is rule number 3? So it is 6 points in a row, all increasing or all decreasing, right? As we expected. So since we have 6 consecutive data points showing a downward trend, so the 6th consecutive data point has been identified as the one influenced by some special cause variation. And if you look at U bar, it is 0.2832, and that is exactly what we also got performing the manual calculation. And then the UCL and LCL values for the 20th day, 0.5046 and 0.0618. So 0.5046 and 0.0618, right? But then if you want to find out the LCL and UCL values for a particular day, so you need to keep the cursor on top of this bar. So for the first day, the LCL value is 0.0133 and the UCL value is 0.5530. So the first day, 0.5530 is UCL, 0.0133 is LCL. Perfect. Right? So let us provide the inference here. So the inference will be there is presence of assignable or special cause variation on the 16th day due to 6 consecutive data points in the downward trend. Right? So we need to analyze the reason for this assignable cause. And take appropriate corrective action. This will be my inference. But then in the assessment, you will not be asked to create any control chart, but you will be asked to calculate the control limits for a U chart scenario. So I've given the template here for calculating the control limits for a U chart scenario, right? So you can just provide the input values and then get the control limits. So let us pick the first day data points. So sample size is 35 and the number of defects is 15 and the historical average, that is the U bar value, is 0.2832. And we get the LCL value as 0.01334. So if you are going to extend this further, so it will be 0.01334 and the UCL value is 0.55306. So extend this by one more digit, you will get 0.55305 or 306 and this will be 0.0133. Perfect. Right? So you'll be asked to calculate control limits for a standard deviation chart, for P chart and U chart. Right? So these are the 3 questions wherein you will be asked to calculate the control limits. So the templates are provided here. So you can just refer to this particular sheet and then use the template. So for standard deviation chart, you already done the calculation. You just need to pick the control limit values. For P chart and U chart, you can make use of this template, provide the input values as given in the question. It will be straightforward and you can pick the control limits right from this template. Fine. So with this, we actually come to the end of this entire training session. So thanks a lot for your cooperation and it was wonderful, bringing in all these concepts to you. I certainly enjoyed all these 12 days. I hope it was a good value add for each one of you. And I'm sure that all of you would actually pick up a project and apply all these tools and techniques and then successfully complete and submit the Six Sigma project document to us to get the project completion certificate. So as I informed on the 10th day of this training session, so I'll be sending the link for accessing the project initiation form, right? So once you start, attempting the black belt final assessment, so I will share the link for accessing the project initiation form. So I'll give you a couple of days for you to fill in that particular form and submit it to me. So once I receive all the forms from your side, so I will collate the email IDs and then send out a common email. So if you are given 2 days time, so you have time till uh, Saturday afternoon or Saturday evening, right? So Sunday, you can expect a mail from me wherein I will send out a common email providing all the details as to how you need to submit the project document. And I will also attach the sample project document along with the project documentation template, right? Again, I repeat, this is not a mandatory exercise. So those who are interested to work on a Six Sigma project may actually, fill in that project initiation form and submit it to me and start working on either a real-time project or a simulation project, right? So all the very best to each one of you and all the very best for the final assessment as well.
Thank you very much.
Thank you. Thank you so much, Sri.
Yeah.
Thank you, sir.
So let me just share the updated files to you to the common WhatsApp group. Just give me a second. I've already sent the procedure for accessing the final test link. It's the same procedure that I shared yesterday. So you can just go through the same procedure and then access the final black belt assessment link. And I will send the updated files to the common WhatsApp group. I've shared both the updated files, so you can start answering the black belt final assessment questions. Again, wishing you all the very best. So as I informed earlier, so I'll be remaining online for the next 60 minutes or so. In case of any clarifications required, you can always connect with me. But then I'll go on mute now.
Hi, Sridhar.
Yes, please.
I have submitted.
Okay, good. So all the very best.
Thanks. Thank you so much.
Thank
And
you.
thanks for the files. It was really helpful, the Excel files.
Thank you. Thank you.
Thanks. Thanks. Can I
You
drop?
can also fill in the feedback
Yeah,
form.
I
So
saw the
which will
feedback.
pop up once you
Yeah.
exit this link.
Yes.
And you can also kind of provide your feedback in the Google review. So I've sent the link for accessing the Google review.
In WhatsApp chat.
Yeah, in the WhatsApp, common WhatsApp group, I just
Yes,
provided
please.
you.
I'll do that. I'll do that. Thank you. Thank you so much.
Thank you.
Excuse me, sir. Which LinkedIn you'll publish that?
So it will be coming from my account actually. So I will be posting it tomorrow.
Okay.
Okay.
Thank you.
Yeah. Thank you. All the best.
Thank you, sir. Thank you. I have completed
Thank
the.
Thanks a lot.
Thank you, sir. I have completed. Sir. Hello. Sir, can you hear me?
Yeah, please.
Yes. Yeah, I have done once I completed.
Good. So all the very best.
Thank you so much, sir. Thank you so much for
Thank
your valuable time, and I'm really admire for your knowledge, and thank you so much for this great opportunity.
Thank you. Thanks a lot. All the best.
Pleasure to meet you. Thank you so
Thank you.
much. Wish you all the best to you. Thanks a
Thank you.
lot. Thank you
Thanks
so
a
much.
lot.
Yeah.
Okay then. So shall I close this batch? So all the very best to all of you. Thank you. Thanks a lot for your support. Thank you.
Thank you, sir. Thank you so much.
Thank you.
Thank you, sir. Thank you so much.
Thank you.